Hi, my name is Nick Borson, and I've been doing a series of videos about learning to program. And in these videos, I've been using PowerShell to walk through some different examples to teach some general programming topics. And in one recent video, which I'll include a link to in the description, was about binary numbers. Computers naturally store numbers in memory as using binary digits, that is bits, instead of the decimal digits we're more familiar with. And there's a few basic things about binary numbers that are helpful for a programmer to understand. And I covered some of those in that video, like just what are binary digits and what's the difference between a 32-bit versus a 64-bit number, say, or an unsigned versus a signed integer, and so on. But as I thought about the topic a bit more, I found that I wanted to maybe dive a little bit more deeply and talk about what binary digits really are, how computers perform operations on binary digits. Why do computers use bits instead of decimal numbers? And it kind of boils down to that operations on bits are reducible to simple logic operations that are very primitive, very fundamental to how computers work. So this video is a bit more of a conceptual thing. I am going to be using some PowerShell because I'll be using it to sort of write a little simulation of how computers actually process bits. We'll start by just talking a bit more about binary numbers, and then we'll walk through how computers can do bit operations in order to add two numbers without ever actually really understanding what addition means. So this video is a little bit more, you don't necessarily have to watch this, you don't have to understand this stuff to learn to program, but I think it's interesting to understand how computers work, and it's not really magic, it's just kind of mechanics of working with bits. So without any further introduction, let's get started. Let's start with a quick review of binary numbers. Binary numbers are very similar to the familiar decimal numbers, except that binary numbers are base 2, whereas decimal numbers are base 10. So with decimal numbers, we have 10 possible digits, 0 through 9, but with binary, we only have 2 digits, 0 and 1. A binary digit is also just called a bit. You may have heard of bits in computing, and a bit is kind of the smallest possible unit of information you can store in a computer because it only has the two possible values, 0 and 1. So since there are only two possible values of a digit, then the place value of each digit increases by a factor of 2 each time you go one digit to the left, as opposed to a factor of 10 in decimal. So the rightmost digit, the least significant digit, is in the ones place, and the digit to its left is in the twos place, and then we have the fours place and the eights place, and so on. As opposed to decimal, where you start in the ones place, and then the tens place, and the hundreds place, etc. We can write these as exponents, so each bit, each binary digit, has an index. We number them starting with the rightmost or least significant bit at index 0, and then the digit to its left is index 1, and so on. Well, the place value of a digit, the place value of a binary digit, is 2 to the index. So the bit 0 is its place value is 2 to the 0, which is 1, and bit 3, for example, its place value is 2 to the third, which is 8. So 2 is the base of all these exponents. That's why you say this is base. These numbers are base 2. Whereas the same system with decimal, it would be base 10. So the value of each place is 10 to whatever the index of that digit is. So let's, considering all that, let's look at these 5 numbers I have here and consider what their values would be. So the first number has a 1 in the ones place and all the other bits are 0. So its value is 1. If we add up all the values of all the digits, then we get 0 plus 0 plus 0 for all those 0 bits, and then a 1 because the least significant digit is in the ones place. The next number, 0010, has a 1 in the twos place. So all the other bits are just 0, and the 1 that's in the twos place has a place value of 2. So when we add that up, we get 0 plus 0 plus 2 plus 0, which is of course 2. And the next one is 0111, so we have 1s in the 4, 2, the 4's place, the 2's place, and the 1's place, and you add those up, you get 7. The next two, we have a 1 in the next number, we have a 1 in the 8th place, the most significant bit of this 4-digit number. And all the other bits are 0, so, so that gives us a value of 8. And the last one, we have all 4 bits are 1, so we add up the place value of all those bits, and we get 8 plus 4 plus 2 plus 1, which is 15. So all the examples in this video, I'm just going to talk about 4-bit numbers, which is pretty small, but that just makes it, you know, when I discuss this further and show some examples, it's easier to work through when we only have 4 bits. In actual integers in computers, typically we have 8, 16, 32, or even 64 bits. So these are all unsigned numbers. What if we were to treat these as signed numbers? So when we signed integers. So with a signed integer, we treat the most significant bit as signifying the sign. So if that most significant bit is 0, then it's a non-negative number. But if the most significant bit is 1, then it's a negative number. These are 4-bit numbers, so the most significant bit is bit 3. So the last two numbers in this example are both negative numbers. So how do we calculate the value of those numbers? You might think, well, okay, the second to last one, if it's negative, would be negative 8, and the other would be negative 15. But that's not how it works. The way that all modern computers do this is if the sign bit is 1, then you subtract, in this case, 16, because this is a 4-bit number. You subtract 2 to the 4, which is 16, from the unsigned value to get the signed value. So let's take a look at these examples. So the second last example, we have the unsigned value is 8, because there's a 1 in the bit with place value 8. If we then, but because that is the sign bit and the sign bit is set, that we then subtract 16 from that, which gives us 8 minus 16, which is negative 8. And the last example, we have all 4 bits are 1. So the unsigned value is 15, like we said, but we subtract 16 because the sign bit is set, and that gives us 15 minus 16, which is negative 1. And that's an interesting case because all the bits are 1. It's always going to work out, even if we have 8-bit, 16-bit, or larger numbers, that if all the bits are 1 and we're treating this as a signed number, that's going to be negative 1. Because the value we're subtracting is 2 to whatever the number of bits is. Let's say for an 8-bit number, it's 2 to the 8, which is 256. And the unsigned value is the largest possible, is all bits 1 is going to be 2 to the n minus 1. So, for example, if it's a byte, if it's an 8-bit number, all bits 1, the unsigned value is going to be 255. And we subtract 256, it's going to give us negative 1. So that's going to be the same pattern is going to hold no matter how many bits we have. If all the bits are 1 and it's an unsigned number, that's going to be negative 1. Okay, so that kind of summarizes how binary numbers are represented, but let's actually do a little demo using PowerShell to see how to kind of simulate how binary numbers work in a computer. Okay, so here I have a PowerShell script open in Visual Studio Code. I've already written this script just to save time, so you don't have to sit here and watch me type. But what this does is it essentially simulates how we might represent a 4-bit number. So we can do our own computations on bits to see kind of how numbers are represented as bits in a computer. So this is a class. So we use the class keyword in PowerShell to introduce a class, which is our own type that we're defining. And this type is called bits4, to represent a 4-bit value, and it has 4 fields. So there are 4 properties in this class. And each of these is of type byte, so this is simply an unsigned 8-bit number. And each of these represents the value of a single bit. So I started with the most significant bit and then downward. So I just numbered them bit 3, bit 2, bit 1, and bit 0. So we simply store 4 bits. We store them as separate fields, each of which is a byte. And I just chose byte because it's the smallest addressable numeric data type. Smallest numeric data type that we can use. But I'm just going to always set each of these to either 0 or 1. So those are, we have our class with 4 fields, and here we have a constructor. This is a member function of the class, but it's a special member function. Its name is the same as the class name, bits4, and that means that this is a constructor. So when we create a new instance of this class, we can specify arguments that are then passed as parameters to the constructor, and we take. So when we're creating a new instance of this class, we're going to pass in 4 parameters, 4 arguments, which are the values of the 4 bits, numbered from 3 down to 0. And inside the constructor, all we do is we assign those to the fields. We have to use the this. We have this. The this variable refers to the object that the constructor is being called on, and then we then can refer to its members, bit 3, 2, 1, and 0. And we set them to the values of the parameters that were passed in. And finally, we defined another member function called toString. It returns a string, and this is a well-known member function because it's the one that is used whenever you want to convert a type to a string. So if we create a bits4 object and we use it in a case where PowerShell needs to convert it to a string, for example, if we include it as a parameter in a string, then this method will automatically be invoked. And all it does is it creates a string with the 4 bits, the 4 fields, bit 3, 2, 1, and 0, embedded in it. So we're using this syntax where we are having an expression within the string that gets expanded, and the value of the expression is, or this is the expression, and so the value of this expression gets inserted in place of this. So the value of bit 3 gets inserted, followed by the value of bit 2, followed by the value of bit 1 and bit 0. So there's our bit4 class. So next, we have a function that will take a regular integer value and convert it into a instance of our bits4 type. So to get the 4, we get the 4 low order bits 0, 1, 2, and 3 out of this integer. And to do that, we use the shift and bitwise and the shift right and bitwise and operators. So to get bit 3, we need to get the bit 3 is at index 3, and we need to shift it down to index 0. So we shift all the bits of the value 3 places to the right using the shift right operator. So what was bit 3 is now in bit 0. And then we use the bitwise and operator to mask off all the bits, so that all the bits go to 0 except for the bit bit 0, because 1 is in the 0's place. So it might help us to review, maybe if you haven't watched another video that talks about this, how the AND operator works. So for example, let's say that the actual value we're starting with is 1101. Okay, so bit 3 would be, so this is bit 0 is the rightmost bit, then we have bit 1, then we have bit 2, and then we have bit 3. So when we shift this to the right by 3 places, then shifting it right 1 place, okay, so this is the value. Okay, I'm going to put in a comment, put this in the form of a comment. So shifting right 1 gives us, we shift in a 0 onto the left to take we get 110. So these 3, this has been shifted, we've shifted right, we shifted right 1, so the low order bit has been shifted off the end. The remaining 3 bits have been shifted over 1 place, so they're now here. And then the leftmost bit has been filled in with a 0. Actually, there are 2 different ways you can fill in the leftmost bit, depending on whether you're shifting it using signed or unsigned shifting. If you're doing signed shifting, then the signed bit gets extended. If you're doing unsigned shifting, then a 0 gets shifted in on the left end. If we shift right 1 again, shifting right by 2 places, then the low order 2 bits get shifted off the end, the next two bits get shifted over two places. So we'd have 0, 0, 1, 1. And if we shift right 3, then the bottom 3 bits would get shifted off the end, and the next bit would get shifted down to the ones place, so like so. So you can see how shifting works. So that's the shifting part. Now notice when we do this, by the way, we don't actually change the value variable. We're just evaluating the result. This expression is giving the result of the result of shifting, but it's not actually changing the value, changing what's stored. It's not modifying the value variable itself. So for example, value, if this is the value is still 1101, but value shift right 3, this expression is going to give us the result of this shift operation. Okay? So now, the bitwise AND. An AND is just going to is going to do like a logical AND between each pair of bits in the two numbers. So if we have 1101, for example, is A, for example, we have two numbers A and B, and we're doing A and B. So A and B. So if A is 1101 and B is 1010, for example, then A and B, and actually the operator is actually, the bitwise AND operator is actually B, A, and D, so we'll just actually write it that way. What we do then is we just take the corresponding bits in each column. So let's take bit 3, for example. Bit 3 of A is 1 and bit 3 of B is 1, so they're both 1. So the AND is true. They're both 1. So bit 3 of A is 1 and bit 3 of B is 1, so the result is 1. But if they're not both 1, in all other cases, this result is going to be 0. So if bit 2 of A is 1, but bit 2 of B is not 1, so the result is going to be 0 because they're not both 1. And likewise for these other cases. Here bit 1 of A is 0, and bit 1 of B is 1. They're not both 1, so the result is 0. And here the reverse is true. The bit 0 of A is 1, but bit 0 of B is 0, so the result is going to be 0. The only case where the result is 1 is with both of the values is 1. So this can be used for what's called masking. In this case, I only want the low order bit of I'm only interested in the low order bit of the result. The low order bit of the I've shifted the bit I'm interested in into bit 0 of this expression gives a value with the bit I'm interested in bit 0. And I want to mask off that bit and set all the other bits to 0. So what I can do is I can AND with a number that only has bit 0 set, in other words, 1. So now if we say this number and 1, we're going to be clearing all these high order bits, because the only bit that could potentially be 1 is this low order bit, because B only has a 1 in that low order bit. So if the low order bit of it is A is 1, the result is going to be 1. If the low order bit of A is 0, then they're not both 1s, so the result is going to be 0. So this, having the 1 here, the B value is being used as a mask because it controls what bits are potentially going to be set in the result. But the bits are only going to be 1 if they're 1 in the value. So we're checking if the lower order bit of this is 1, and what they're doing that by masking off just that bit, by bitwise ANDing it with 1. So anyway, the end result of all that is bit 3 is 1 if the bit 3 variable is going to be 1 if bit 3 of value is 1. Because we're shifting that bit down to bit 0 and then masking it off. Bit 2, the bit 2 variable is going to be 1 if bit 2 of value is 1, because we're shifting that bit down to bit 0 by shifting the whole thing right 2 bits and then masking off just the low order bit. And bit 1 is going to be 0, excuse me, is going to be 1 only if bit 1 of value is 1, because we're shifting that bit into bit 0, shifting everything right one place so that what was bit 1 is now in bit 0, and we're masking off that bit. And then finally, in this case, bit 0 is going to be 1 only if bit 0 of value is 1. We don't have to shift because the bit we're interested in is already in bit 0. We just have to mask off that bit. Okay, so we've done all that. I'm going to go ahead and erase these extra comments here. So when we've done all that, we have the separate variables that represent the values of bits 3, 2, 1, and 0 of the parameter. Then we can create an instance of our object. So we use the new object command. We give the type name is bits4 because that's the name of the class we created. And then we use the argument list to pass the 4 bits we're interested in, bits 3, 2, 1, and 0. They're separated by commas. This is actually an array right here. Okay, so bits 3, 2, 1, and 0 are passed as an array to the argument list command, as the argument list parameter to new object, and then they're passed. The elements of that array are then passed as individual parameters to the constructor. So what bits 3 here then becomes the parameter, the b3 parameter of the constructor, and bit 2 becomes the b2 parameter of the constructor, and so on. And in that way, the new bits4 object we create has the individual bits, these properties set to the values that we computed above. That new object then is going to be the output of this command is then going to be the output of our getBits function. So by calling getBits with a number, it's the output of this function, the return value of this function, is going to be a new bits4 object that has its individual bit fields set to the low order 4 bits of the value that we passed in. Okay, so I have 2 more things here. This is kind of doing the reverse of what we did above. This is converting from a regular integer to, we're essentially unpacking the 4 bits of this integer and converting it into a bits4. And here we're doing the reverse. We have a bits4, and we're going to convert that to an unsigned integer. And this is taking advantage of the place values that we talked about a moment ago. So bit 3 is in the 8's place, bit 2 is in the 4's place, bit 1 is in the 2's place, and bit 0 is in the 1's place. So we multiply bit 3 by 8, and we multiply bit 2 by 4, we multiply bit 1 by 2, and we don't multiply bit 0 by anything. And of course, each of these bits is either 0 or 1. We add all those up, and the result of that is the unsigned value of that 4-bit number. I can make this a little wider so we don't have to. Okay. So that is how we that's exactly what we looked at when we were saying how do we interpret the unsigned value of a number. Then to interpret the signed value, we do that same thing. We get the unsigned value, but then if bit 3 is non-zero, if bit 3 is 1, then we know that this is a negative number, so we subtract 16. Again, this is a 4-bit number, so we subtract 2 to the 4th, which is 16, and that result of that is going to be the signed value of that bit pattern, and we return that as the return value of this function. Okay, finally, so we have a little our little test function here, and we're just going to take 16 values from 0 to 15, and we are going to call getBits to create a bits4 object from that number, and then we're going to output that by, so for each of these 16 values, for each number 0 to 15, we're going to execute this code block. This code block is going to get a bits4 object from that number, convert that number to a bits4 object, and then pass that to this function, format bits. Pardon me. So format bits is going to output the bits themselves. So this is using the format operator of a string. So this is a format string, and each of these expressions, each of these things inside of curly braces is a format specifier. The format specifier begins with an argument index. So this 0 then is referring to this argument, the first argument after the F operator, which means format. So we're going to be inserting the value of bits in place of this format specifier. And in order to do that, it has to be converted to a string. And since this is a bits4 object, it's going to invoke the toString method of our bits4 class, which, if you recall up here, is just going to insert the values of bit 3, bit 2, bit 1, and 0. So it's going to actually show the individual bits. Okay. Then here we have another format specifier. The 1 is an argument index. So now that's going to be the return value. That's going to be the result of this expression. So we're going to pass our bits4 object to the getUnsigned method, which is going to give us an integer that is the unsigned value of those 4 bits. Remember, we're just multiplying bit 3 by 8, multiplying bit 2 by 4, multiplying bit 1 by 2, and then adding all those up and multiplying bit 0 by 1, or not multiplying it at all, and adding those all up, and that's going to be our unsigned value. Well, that's going to be inserted in place of this format specifier. And the comma 3 just means we're going to the width of this is going to be 3. It's going to pad this with zeros so that things will line up nicely. And then finally, the last format specifier, the index is 2. So this is the argument at index 2, and this is the same. Excuse me. This is the same thing. We're going to get the signed value. We're going to convert our pattern of 4 bits to a signed number, and that's going to be inserted in place of this format specifier. And again, we're setting the width of the field to 3 just so that the numbers all line up nicely. Okay, so then we're going to invoke our test count method. So for each of these numbers, 0 to 15, we're going to create the object and we're going to format it in this way. So let's go ahead and run our script. And I'll say bits and run it. And here we have our numbers 0 through 15. So indeed, if we've converted each number 0 to 15 to a bits object by storing the individual bits, and we can see that these are the bit values. So bits 0 just converts to 0, 0, 0, 0. 15 converts to 1, 1, 1, 1, and so on. And when we convert them back by multiplying the bits and adding them up, then we get the numbers we expect, 0 through 15. And then when we interpret them as signed numbers, then we just subtract 16 from each of these. So here we have 8 minus 16 gives us negative 8, 9 minus 16 gives us negative 7, 10 minus 16 gives us negative 6, and so on. And of course, 15 minus 16 gives us negative 1. All bits 1 is always going to end up negative 1. And what's interesting about this is that if you count up the unsigned numbers, count up from 8 to 9, that's going to always be, each number is going to be 1 greater than the number above it, right? Well, that's also true for the signed numbers. You count the same bit operations, the same changes of bits that it counts up in the unsigned numbers is also counting up in the negative numbers. So that's kind of interesting. Okay, so let's we've studied a little bit about how binary numbers are represented as bits, but you might wonder why represent them this way, and what do computers actually do with those bits? How do they process those bits? How do they perform arithmetic on those bits? So that's what the rest of this video is going to talk about. All right, so we've seen how to represent numbers as bits, as binary digits, but how do we actually do something with those bits? How do we teach a computer to do addition, for example? Well, if you want to teach a human to do addition, it's something like this. When we teach children in elementary school, then we say something like, well, you have 3 apples, and then you add 2 more apples, and how many apples do you have altogether? So this is building on our intuition. So we start with counting, and we sort of learn to understand numbers in terms of counting. We have this sense that the number of something is how many there are. We have some notion of what that means in the real world. And we build on that to kind of get a notion of adding as just sort of a form of counting, counting up putting 2 sets together and counting up the whole thing. So we understand the meaning of addition. When humans learn to add, we learn what it means in terms of some concept of number and adding and so on. So what about a computer? No, that's not really the way a computer does it. Computers don't really have to understand. They don't understand what numbers are. They don't have this intuition we have of what adding is and numbers are. When we teach computers to add, we don't teach them to understand what adding means. All we care about is that when computers manipulate these symbols that represent numbers to us, these symbols represent numbers to us. So computers, they just manipulate the bits, and all that we care about is if after that manipulation, it gives the right result. The result that to us is the sum of those numbers. So computers are not very good at understanding numbers or understanding what addition means, but they're very good at manipulating these symbols, manipulating bits. And they do it through something called logic gates. So a logic gate is a component of a digital circuit. It's actually a physical part of a circuit on a chip that takes some inputs. Each of those inputs is 1 bit, and it produces some outputs. And those outputs are 1 bit. And actually, when we're talking about a physical gate on a chip, those inputs are represented in some physical way. So they were typically, in an electronic computer, we're talking about voltages. So one voltage level would represent a 0, and a different voltage would represent a 1. So you have a component on a chip, and maybe you have 2 inputs and 1 output. And if the 2 voltages are set a certain way, then we interpret that as being a 0 and a 1, and then the output is going to be either a 0 or 1, depending on what particular operation that gate performs. And there are different kinds of gates that will do operations that we can interpret as being different Boolean operations, like not, and, or exclusive or, XOR. So, and by the way, this illustration on the right is simply a commercially available chip that is a very simple chip. All it contains is 4 NAND gates. NAND is one kind of logic gate, and all this chip contains is 4 NAND gates and allows you to wire them up by connecting the pins however you want to with wires. It's a very simple chip. In something like a microprocessor, the brains of your phone or PC, there are probably billions of logic gates that are all wired up in a certain way in order to implement the functioning of that microprocessor. Okay, so I mentioned NAND gates. NAND stands for not and it's actually a very fundamental gate, because if you have a NAND gate, it is possible to construct all the other Boolean operations from it. So this is one of the most, there's one other gate that has this property called NOR, but I think NAND is probably used more often. So if you have the ability to construct a NAND gate, which you can do using just 4 transistors, then you can build up any other kind of logic gate from some combination of NAND gates. So what is NAND? Well, like I said, it stands for not and that's because the result of the NAND is true only if it's not the case that both of the inputs are true. So we can represent this with a truth table, and a truth table looks like what I've shown here at the top. So we have the first 2 columns are the inputs. We just label the inputs A and B, whatever you want to call them. And then on the right-hand side, the last column, we have the value of the output of A NAND B, of the result of the operation, depending on that particular combination of inputs. So for example, if the inputs are 0 and 0, then A NAND 0 and 0 is going to be 1, because it's not the case that both of these are 1. So if either of if the inputs are 0 and 1, again, A NAND 0 and 1 is going to be 1. If the inputs are 1 and 0, A NAND 1 and 0 is also 1. And if the inputs are 1 and 1, then this is the only case where the output is 0 because 1 and 1 is true, so not and 1 and 1 is false. Okay, so that's a NAND gate. And the ANSI symbol for a NAND gate looks like this. It's sort of a, I don't know, a little half circle with a little circle on it. The little circle means not, essentially. So the symbol for an AND gate looks like just this part, and then you put the little circle on it, and you have NAND. So like I said, once you have a NAND gate, you can define any other logic gate in terms of some combination of NAND gates. So to take a very simple example, you can define NOT in terms of NAND. So NOT is only has one input, and it returns the complement, the logical complement of that. In other words, the opposite, if you will. So if A is 0, then not A is 1. And if A is 1, then not A is 0. That's kind of what you'd expect from NOT. So it's possible to define NOT in terms of NAND. So and the relationship is simply that not A is going to be the same as A NAND A. And we can see that if we again look back at the truth table for NAND. Well, okay, so let's say A is 0. Of course, there are only two cases. A is either 0 or 1. If A is 0, then what would 0 NAND 0 be? Well, let's look at the truth table. 0 NAND 0 is 1. And that's what we expect if A is 0 for NOT. Now, if A is 1, then what is 1 NAND 1? Well, we can look at this table. 1 NAND 1 is going to be 0. And that's what we expect from NOT 1. So it works out that NOT A is the same, is going to be equivalent to A NAND A. And that allows us to define a NOT gate by just wiring it up so that that one input, A, goes into both the A and B inputs of the NAND. So here's the A input of the NAND, the B input of the NAND. We just wire that A input up to both of them. So we have A NAND A, and the output of that NAND is going to be the output of our NOT. So we've defined NOT in terms of NAND. And this, by the way, is the ANSI symbol for NOT, for a NOT gate. Okay, so those are NAND and NOT. Some other common logic gates. These are the truth tables for some other common logic gates. We've already discussed NAND. AND is going to give us 1 only if both A and B are 1. In all other cases, it's going to be 0. Kind of makes sense, what you'd expect from AND. Or it's going to give us a 1 if either A is 1, B is 1, or both are 1. So the only case where OR is going to be false is if neither A nor B is 1. Okay, that's kind of what you'd expect from an OR. And then XOR is also a common one. It stands for exclusive OR. It means either A or B, but not both. So if neither is 1, then A XOR B is going to be 0. And if both are 1, then A XOR B is also going to be 0. So that's where it differs from OR. But if only one of them is 1, then A XOR B is 1. Okay? So those are some common logic gates. All right, so having discussed logic gates, let's get back to our question of addition. So, like I said, when we are teaching a computer, teaching in air quotes here, a computer to add, we're not trying to get the computer to understand addition. All we're trying to do is manipulate the bits in such a way that the output is going to be the sum of the two inputs. The pattern of bits we get for the output is going to correspond to the numeric value that is the sum of the pattern of bits. To the computer, these are just patterns of bits. And we want the patterns of the output to be such that when we interpret this as a numeric value, this is the sum of these two numbers here. Okay? So we can try to think of that in terms of bit operations. Well, let's think about how we add numbers ourselves. When we do addition, we simply add the columns. We start with the least significant column, and then we add those, and then we kind of move our way to the left. So let's start with the least significant column here. We'll start with bit 0, and we add these two bits. So we can think of this as a bit operation with two inputs, right? There's going to be this bit and this bit 0 of each of these numbers, and it's going to produce an output, which is the sum of those two bits. But the sum can be 0, 1, or 2, right? We have two 1-bit numbers, so the sum can be 0, 1, or 2. And if it's 2, then we're going to have to carry a value over to the next column, right? Because we can't fit a 2. So if it's 2, the sum is going to roll over to 0, and we're going to have to carry a number over to the next column. So we need to define some sort of component made up of logic gates so that we have two inputs and we have two outputs. One of those outputs is going to be the sum that gets put in the corresponding column here, and one of those outputs is going to be the carry bit. Okay, so this component is called a half adder. In electronics, there's a component called a half adder that does exactly what we're talking about. And we can think of this as just another Boolean operation, another operation on a logic operation on bits. And as with other logic operations, we can define what we expect of it in terms of a truth table. So we have two inputs. We have A and B, and those are the two bits that we're adding. And then we have our carry that we're carrying over to the next column, and we have our output bit that we're going to be writing in the column in the corresponding column of the result. So the only case where we're going to carry a number over to the next column is if the result is 2. So if both A and B are 1, then the result's going to be 2. We're going to have to carry a bit over to the next column. So all other cases, the carry is 0. Okay, so that's pretty simple. And then for the output, we simply count them up. So if we have 0 and 0, 0 plus 0 is going to be 0. If we have 0 and 1, well, 0 plus 1 is going to be 1. If we have 1 and 0, 1 plus 0 is going to be 1. And if we have 1 and 1, 1 plus 1 is 2. But in that case, this rolls over to 0 because we're carrying the 2 over to the next column. In effect, we can think of this as being a 2-bit result. So this is binary 2 because 1, 0 is 2. So we're going to carry that 2 over to the next column. Okay, so now we can think of we can treat each of these columns separately and think, well, what is a binary logic operation that corresponds to the mapping of these two inputs to that particular column? Well, for C, if we look at this, it's the same as an AND, right? C is going to be 1 only if A and B is 1. So C is equal to A and B. And if we look at this, the output is going to be 1 if A or B is 1, but not both, right? So this is the XOR operation. So C is just equal to A and B, and out is equal to A XOR B. So a half adder is simply defined in terms of the AND and XOR gates. So returning to our addition problem, we can start by, to add two numbers, we can start by using a half adder to add, if you will, to process these two digits, and we store one of the outputs in this column, and then we store the other output in a carry value that's going to carry it over to the next step of our addition. So the next step of our addition is where we add the next column. When we add the next column, we have a little bit more complicated step because now we have the carry bit to worry about. So we're going to have to add the two bits in bit 1 of the first number to bit 1 of the second number, but we also have to add the carry bit, right? So we're adding three bits instead of 2. And when we add those 3 bits, we're going to get a result that's going to be in the range 0 to 3, right? It could be 0, 1, 2, or 3. But again, it's going to be a 2-bit result because we may have to carry, if the result is greater than 1, we're going to have to carry a bit over to the next column. If the result is 2 or 3, that is, we have to carry a bit over to the next column. And then, of course, we have the actual bit in this column. So the operation that performed the addition of just 2 bits without any carry was called a half adder. You may guess that the component that performs an addition of 3 bits, including a carry bit, is called a full adder. So in here we have 3 inputs instead of 2. So we're adding the 2 bits A and B of the numbers that we're adding, and then we're also adding the carry bit from the previous column. And so those are our 3 inputs. And then we're doing a Boolean operation on those 3 inputs to produce 2 outputs. And instead of numbering them out and C, I've just numbered them S0 and S1 because you can think of this as being essentially a 2-bit result, right? We're essentially computing a number in the range 0 to 3, and we need 2 bits to store a number that large. So this number is the one that's going to be, the S0 is the number that's going to be in the current column of the output, and S1 is going to be the carry bit that's going to be carried over to the next, when we add the next column. Okay, so again, we're adding 3 numbers, so we add 0, 0, and 0, and the result is just going to be 0, right? We add 0, 0, and 1, add those up, we get 1, and the result is going to be a 1 in S0. It's going to be essentially the binary number is going to be 0, 1. We add this, again, we just have 1 bit, so we have 1. Here we have 0, 1, 1. Well, 2 of those, we add those up, add those individual bits. We have 1 plus 1 is 2, and binary 2 is just 1, 0. So we're going to be carrying, we're going to set the carry bit, or S1, to 1, and the low order bit is going to be 0. And here we have, again, just 1 plus 0 plus 0, and that's going to be 1. 1 plus 0 plus 1, that's going to be 2. So we're going to be, again, going to be setting the carry bit. So this is essentially, again, a 2-bit result. Binary 1, 0 is 2, so we're going to be setting the carry bit to, or the S1 output to 1. And here again we have 1 plus 0 is 2, so same thing. And then this, of course, if all the inputs are 1, we're carrying a 1, and both the input bits are 1, we have 1 plus 1 plus 1 is 3. And so we have a 1 in both columns, a 1 in the output, and we're carrying a 1. So that's binary 3. Okay. So again, we can just think of each of these columns independently. If we look at S0, I'm not going to try to explain it all, but it works out that S0 always comes out correctly if you compute it as A XOR B XOR C. And we can take a couple examples to see that. So for example, A XOR B, if we look at this one, A XOR B is going to be 1. Remember, XOR is one or the other, but not both. So A XOR B is 1, and then and then the result of that, 1 XOR C is going to be 1 XOR 0, which is also 1. So the result is 1. So that's what we expect for S0. And to take another example, here we have A XOR B XOR C. Well, A XOR B, 1 XOR 0 is 1. So then this A XOR B is 1. So then 1 XOR C, 1 XOR 1, is going to be 0 because they're both 1. And XOR of 1, 1 is going to be 0. So then we get a 0 in the output. So this is also what we expect for this operation. So it works out that this combination of operations is always going to give us the result for this column. And by the way, there are other ways to implement a full adder. This is just one way that works. And again, this combination of operations works for doing the S1. And I won't go through a bunch of examples or anything, but it works out that one way you can construct, you can produce the correct output for the carry bit, or the S1, I'm calling the S1 here, the sum, bit 0 of the sum and bit 1 of the sum is by doing this combination of operations. Okay, so we have our full adder. So we add these two numbers plus the carry, and we get bit 0 of the sum goes in the output column, and bit 1 of the sum gets carried over to the next column. And again, we just used another full adder to take the output of the previous columns additions, or the carry from the previous columns additions, and then add these two columns. And in this case, for example, we've adding this has given us 2, and so we've gotten a 0 here, but we've carried 1. So now we have 1 plus 0, which gives us 1, and then we don't carry anything. So then when we go to the next column, we again have a full adder. Carry now is 0, so 0 plus 0 plus 0 gives us 0. And when we add the last column, we don't use the carry, so we just don't wire up the carry output to anything. So this kind of shows how using a combination of full adders, or half adders and full adders, a combination of components that are just built up out of logic gates, that a computer can add two numbers And all it's doing is it's performing very simple primitive operations on bits. It doesn't understand what those bits means. It doesn't understand what numbers means. But it works out that if you wire this all up correctly, that the pattern of bits of the output actually represents the sum of the two numbers that were the two inputs. So that is how computers do addition. Let's now dive into PowerShell a little bit, and we can actually extend our little simulation to show how addition can work on some 4-bit numbers. Just discussing how computers can actually do addition by performing some manipulations on bits. Let's now return to our PowerShell script and extend it to demonstrate those same bit manipulations and see how it actually works out. So remember, we had our. I'm going to comment out our little little call to the test count function here, because we're going to skip that part and go on to doing addition. So if you recall, the half adder and full adder both had 2-bit outputs. So I added another class here, which I called bits2, that just represents a value that just contains 2 bits. So we have a bit 1 and bit 0. And we have a constructor that takes these, that has 2 parameters called b1 and b0. Those are the values of the 2 bits. And all the constructor does is it stores those values in the 2 fields, the 2 properties that we've defined. Okay, and then again we have a toString method. This is the method that gets invoked automatically if we ever want to take a bits2 object and convert it to a string. Then the string we return is just a string that has bit 1 followed by the bit 1 property of this, followed by the bit 0 property of this object. Okay, so there is our bits2 class, and we're going to use that. That's going to be the return value of our half adder and full adder. So, we're not actually constructing real logic gates here, but we can get the same concept across by just writing functions that do the same operation that the logic gate does. So this is the truth table for our half adder. So we have, remember, we have the half adder, we just have 2 1-bit inputs, the 2 bits we're adding, and we have what amounts to a 2-bit output. We have the sum of the 2 bits, the low order bit of the sum of the 2 bits, and we have the high order bit, which is the carry bit, right? And the only case where the high order bit is set is if the sum is 2, because in that case we have to carry a bit over to the next column. In all other cases, the high order bit is 0. And the sum is going to be 1 if either A or B is 1, but not both, because in the case where it's both, then the sum is 2, and so we have to roll over to, have to carry a bit instead. We roll over to 0 and carry a bit. Okay, so it worked out, as we discussed before, that that S1, the carry bit, the higher order bit of the sum, is the same as the AND of the 2 inputs, bitwise AND. So we can just use the bitwise AND operator. And it worked out that bit 0 is the bitwise XOR, the exclusive OR of the 2 inputs. So we can just set S0 to the XOR of the 2 parameters, right? The 2 parameters correspond to the 2 inputs of our simulated gate, if you will. And we're going to create a new instance of our bits2 class, and we pass the 2 values of the bits, S1 and S0, as the argument list. So those end up getting passed to our constructor and stored in the 2 fields, bit 1 and bit 0. So we end up, the return value of this whole thing, of this half add function, is going to be a bits2 object that contains the bits, the high order bit, which is the carry bit in bit 1, and the low order bit, which is the output bit for that column in bit 0. So that's our half add function. So I wrote a little test function that just tests the half add function all by itself. And so we just consider, for each possible A in the range 0 to 1, so it's either 0 or 1, and for each possible B in the range 0 to 1, then we just call our half add with A and B, and then we output the result. And this sum in this case is going to be a bit 2, so the half add is returning a bit 2 class. So sum is going to be a bit 2 class. So when we use it in a string like this, the value of the bit 2 is going to get converted to a string using our toString method. So it's just going to take the 2 individual bits and put those in here. Okay, so this is our half add function, and we have a little test method just to see if it works the way we expect. Essentially, what we get here when we run this should be something very much like the little truth table we have in our comments up here. So let's run this script, and we'll just say bits, and what we get is 0 plus 0 is equal to this pattern of bits 0, 0, and that's what we expect. 0 plus 1 is equal to the same pattern of bits. This is binary 1, right? 1 plus 0 is also equal to binary 1 because that's the sum of 1 plus 0 is the same as 0 plus 1. It's just 1. And if we get 1 plus 1, that's 2. So that means that our high order bit, our bit 1 of the result is 1. And the low order bit of the result is 0 because binary 1, 0 is 2. So the 0 is going to be in the output column of the addition, and the 1 has to be carried over to the next column. So that's our half adder. And we've tried our little test program, and we found that our half adder works the way we expect. So we can do the same thing with a full adder. And again, we already looked at the truth table for the full adder when we were kind of doing our little overview of addition. And we have this set of operations defines what the output is. So again, now the full adder, we have 3 inputs instead of 2. We have the 2 bits we're adding, and then we also have the carry bit that was carried over from the previous column. And when we add those all up, then we get a 2-bit sum, a sum that can be from the range from 0 to 3, and we can represent that as a 2-bit number. Okay, so the low order bit, bit 0, it works out that we can just calculate that as the XOR of A and B, and then the result of that XORed with C, and that works out to be S0. And then one way we can get the higher order bit is to do this whole series of operations. Okay, so this code just does exactly that. Now, one thing to note here is that A XOR B appears in 2 places, right? It's here, and it's also here. So we can just do that operation once. We can take A and do the bitwise XOR of A and B, and we store that. Here we're just storing that in a variable. And then we take the result of that, of A XOR B, and we XOR that with C, and we store that in S0. So that's A XOR B XOR C stored in S0. And here we're going to do this. We're going to say A, and then do the bitwise AND of A and B. And then the result of that, we do it as a bitwise OR with this whole expression, which is C bitwise ANDed with the result of A XOR B, which we already computed above. Now, if we were doing this in hardware on a computer chip, then what we would do is we could create an actual XOR gate, and we would wire the A and 0 pins, or excuse me, the A and B pins as inputs to this XOR gate, and then the output pin of this XOR gate is kind of like this variable here, right? The output pin of this XOR gate would then be wired up to the input pin of another XOR gate, so that the output pin of this gate would be wired up to one input pin of this gate, and then the C input pin would be the other input pin of that, and then the output of this gate would be the S0 output pin of the whole thing. So anyway, the way we're doing this in software is very analogous to the way that it could be done actually in circuitry on a computer. Okay. And then when we're done with all this, we have our S0 and our S1 values, and so we create a new object again of type bits 2, and we pass the S0 and S1 and S0 as our argument list. So those are passed to the constructor of our bits 2 class, and the bit 1 and bit 2 properties then take on these 2 values. Okay, so now we can test our full adder the same way we tested our half adder. So for each value of A in the range 0 to 1, and for each value of B in the range 0 to 1, and for each value of C in the range 0 to 1, then we invoke our full adder with this particular combination. Note that these are nested loops, so we're saying, like, we say for A being 0, then we consider all the B's and all the C's for A being 0. Okay, and then we go on, after we've done all these combinations, then we go back to all the combinations where A is 1. And then likewise, when A is 1, say, then we say, okay, let B be 0. And then let's try all the combinations of C where A is 0 and B is anyway, you get the idea. Anyway, so the number of iterations of the nested loop is actually, so the number of iterations of the top loop is 2. And then for each iteration of the top loop, we do 2 iterations of this loop. So that's a total of 4 iterations. And for each iteration of this loop, which is going to be 4 in total, we do 2 iterations of this loop. So we're doing a total of 8 iterations, 2 times 2 times 2, of the innermost loop. Okay, anyway, and then when we do that, we're going to take this particular combination of values, A, B, and C. We're going to invoke the full add function, and we get back our bits2 object that has the sum that we obtained using the method we described above, essentially the result of our full adder gate, and we output that. So the output here then should match very closely what we put in our truth table here. So let's uncomment our little call to the test full add function and run it and see if we get what we expect. And indeed, that's exactly what we get. So we add 0 plus 0 plus 0 is 0, 0 plus 0 plus 1 is 1, 0 plus 1 plus 0 is also 1, 0 plus 1 plus 1 is 2, which in binary is 1, 0. 1 plus 0 plus 0 is 1, 1 plus 0 plus 1 is 2, 1 plus 1 plus 0 is 2, and of course, if all 3 inputs are 1, if both A and B are 1, and the carry is also 1, we get 3, which in binary is 1, 1. So there's our full adder. So finally, let's comment that back out. Finally, let's look at the whole thing where we add 2 numbers together, 2 4-bit numbers together, using a combination of a half adder and some full adders. So first, we just we add bit 0 of the 2 numbers, of the 2 input numbers. Again, we're taking 2 4-bit numbers as inputs. We take bit 0 of each number, we add those together by invoking our half adder, and that gives us a bits 2. So this is a sum 0 is a 2-bit value, right? So now we're going to invoke the full adder. So we take bit 1 of A and bit 1 of B, and we also add, and then we also add the carry bit from the previous column, which is bit 1 of sum 0. So sum 0 being the sum of column 0, we take the carry bit, which is bit 1 of that previous column. So we add those 3 bits up, and we get the sum for column 1. Okay. Then to add column 2, we add up bit 2 of A, bit 2 of the first input, bit 2 of the second input, so bit 2 of A, bit 2 of B, and we add the carry bit from the previous column again, so bit 1 of the previous column. So that's our full add. So those are the inputs again to another full add gate, if you will, or in our case, a full add function. And the result again is a 2-bit result. So there are 2 output bits, which we've represented as a bits 2 object. And finally, we do our addition for the last column. We add bit 3 of the first input, bit 3 of A, with bit 3 of B, and we also add the carry bit from the previous column. So in other words, bit 1 of sum 2 being the sum of the previous column, the carry bit being bit 1. And the result is, again, a 2-bit value, which is sum 3. And finally, the whole thing then is represented as a 4-bit number. So we create a new bits 4 object. And the 4 bits are bit 0 of the third. So this is bit 3 of the sum, right? Bit 3 of the sum is bit 0 of the last column's addition, and then we have bit 0 of the previous column's addition, column 2 addition, bit 0 of the first column, column 1 addition, and bit 0 of column 0 addition. Right. So these are not, we're not adding the carry bits now. We're adding we're not using the carry bits. We're using the bit 0 of each addition. So we add all those up, and we get our 4-bit number, and we can test that in much the way we did previously. So we'll just consider a few different numbers here. So for A, we'll just try 4 different numbers, 1, 3, 5, and 10. And for B, we'll try 3 different numbers, 1, 10, and let's throw in a negative number, 1, 10, and negative 3. And so for each combination of those, we're going to convert A to a bits 4 object, and we're going to convert B to a bits 4 object. So we're just starting with integers here. We're going to convert each of those integers to a bits 4 object, so we have a pattern of 4 bits. And we're going to call our add bits method to simulate the addition using the process we described. And we'll get a result, which is again is a pattern of 4 bits. Now notice nowhere in here are we doing any addition. We're not using a plus operator anywhere in here. We're just doing bitwise operations. We're doing XORs and shifts. Actually, we're basically just doing XORs and ANDs. And yet the result is going to be summing, because by just manipulating bits in certain ways, what we get is going to be addition. Okay, so what we do is then we output we're just going to output something that's formatted so that we can see the way we're adding. So we're outputting. Let's see. Well, we've computed our sum. So we've converted the A to a 4-bit value, converted B to a 4-bit value. We've computed our sum, and then we're just going to write some output. We're going to write the value of A using the format bits class, or the format bits function we defined earlier. We're going to output B using the format bits function we wrote earlier, and we're going to add those. We're going to write out then the sum right below that. So let's try running that. We're going to uncomment this function, and let's run our script one more time. And here's what we get. Okay, so I'm going to scroll back up so we can see them all. So we started by adding 1 and 1, and we get 2. So we have this pattern of bits, and we've just done our bitwise operations. And by just using our half adders and full adders all wired up a certain way, we indeed get 2. And when we convert that back to decimal, that's what we see. We add 1 and 10, and we get 11. Okay. So, and again, we're just doing, we just used the half adders and the full adders, and which were built out of logic gates, and ended up with a certain pattern of bits. As far as the computer is concerned, all we're doing is basic logic operations on bits. There's no math here really per se, except that basic Boolean logic. And yet, when we take a bit pattern representing a 1 and a bit pattern representing a 10, and we put it through our little machine there and turn the crank, what we get is in fact a bit pattern representing 11. And if we interpret those same exact bit patterns as negative numbers, then the bit pattern representing 1 is added to the bit pattern representing -6, because the bit pattern representing 10 as an unsigned number, unsigned 4-bit number, is exactly the same as the bit pattern representing -6 as a signed 4-bit number. And we did the same exact sum. It's the same bit pattern, but the sum comes out to -5 instead of the same bit pattern represents an unsigned 11 when treating it as a signed 4-bit number is equal to -5, and it works out beautifully because 1 plus -6 is in fact equal to -5. So that's part of the genius of this particular way of representing negative numbers, is that many of the same exact operations on signed numbers, that if you do the operations on for unsigned numbers, you can do the exact same operations on the same patterns of bits, and it produces the correct result for signed numbers as well. And we see the same thing in other cases. So 1 plus 13 is 14, and if we do the same exact operations on those bits, but we treat them as signed, it actually has the correct result there as well, because 1 plus -3 is in fact -2. So 3 plus 1 is 4. 3 plus -6, 3 plus 10 is 13. And if we interpret this as unsigned, we get 3 plus -6 is -3. So all these cases do exactly what you expect. and it's all done without the computer knowing anything about addition. All it knows is how to manipulate bits. So that kind of gives you an idea of how computers work at a fundamental level. They really don't have to understand math to do math, because we can break the operations down into fundamental, very primitive operations on bits that it's just machinery that produces a result that matches what we want for those mathematical operations. So thank you for watching this video, and I hope to see you next time.